Hey, what's up, guys? Yeah, so today let's talk about the algebra and root system. So the basic idea is that the classification of the simple Lie algebra finally will become a root system. So let me just quickly give you the background idea. And this video, the main focus of this video is that we derive so-called admissible configuration of the algebra and root system, and find in the next video that we can try to prove that all these thinking diagrams are all possible configuration. Okay, so before, let me just quickly, if you have any question, you can refer to my previous algebra. Okay, so the idea is that, so usually people study the algebra over complex number. And after the big machinery, like Cartan subalgebra, or basically the representation, and also some classification, one can show that one will rather study this special type of algebra called semi-simple algebra. And this type of semi-simple algebra can be shown as used as the direct sum of so-called simple algebra. Okay, so this is the large story that I will introduce in the later, but just believe me that this is true. And finally, one can show that the simple algebra will one-to-one corresponding to the so-called classification or root system. Okay, so once you believe this, then this becomes a geometrical, just some combinatorics and geometrical problem. Okay, so in this video is that let me just tell you that what's root system, and once you believe the root system, and you combine some simple linear algebra, then you can try to show that these are all true. Okay, these I copied from Wikipedia. So you start from the Euclidean vector space, basically the Rn, and you have inner products. So in this video, I will use a bracket as the inner product, and satisfy the following condition: the root system span E, the only square alpha phi, alpha belongs to phi, that belongs to phi are alpha itself in negative alpha. And for every alpha belongs to phi, set alpha is closed under multiplication through the hyperplane perpendicular to alpha. Okay, so this is the same as sigma alpha beta defined to be this. This should be closed. So in my notation, I use this bracket. Okay, and also you don't use this. We just need we tell you that this must be integer. Okay. So these are the common definition. These are definition of root system. Okay. So we believe all these are true, and then we start to see what we can get. Okay, so first is lemma. Okay, so this lemma is very simple, because we know that this must be integer, and this must be integer. So we tell you that we can do their products. So their products will be this. Must be integer. So suppose I define a cosine theta to be the cosine is theta to be the angle between A and B. So alpha and beta vector. So you can view alpha and beta are vector, and their angle is this cosine theta. And obviously that this is 4 cosine theta squared. Okay, so that's equal to 4, right? Because it's our positive. So cosine theta squared must be 0, 1, 2, 3. Sorry, this. Okay. Okay, so which tell you that you have the following situation. The first one possibilities is beta are beta corresponding, or beta are orthogonal to alpha. So which means that cosine theta is 0. Okay, and if this cosine theta is 1 divided by 4, means that alpha and beta, their angle between them is pi divided by 3 or 2 pi divided by 3, because your cosine theta is 1/2. Okay, and you if you plug this, then this be half, this will be integer. So which tell you that beta and alpha must be has the same length. So we have this and this. Okay, and the next is that if cosine theta squared equals to half, means that the alpha and beta has angle pi divided by 4 or 3 pi divided by 4. Okay, and in this case, for example, we have this. So this guy will be alpha beta cosine theta beta squared will be 2 alpha divided by beta. So cosine is this one. This one must be a half integer. Okay, which tell you that alpha and beta, alpha should be, if you divide this, right? So alpha should be square root of beta, or beta should be square root of alpha. So their length must be square root of 2 times. There, this is a ratio. So we have this and also this. Okay, and the next situation is that we have cosine theta squared equal to 3 pi divided by 4. Sorry, 3 divided by 4. So which tell you that is cosine theta is square root of 3 divided by 2, which means that alpha and beta has angle 30 degrees, so it's pi divided by 6 or 5 pi divided by 6. And you can easily show that square root of alpha must be square beta, or beta equals to square root of 3 alpha. Okay, and the final one is that beta is positive negative alpha. Okay, and in this case, your cosine square is 1. Okay, so these are all comma. These are just the comma results that you can derive from these 4. Okay, now so we only have such a situation, right? So the next is that we need to define a so-called regular. Okay, so let's call H belongs to Rn is regular if it's not orthogonal to any roots. Okay, so you find a vector which is you find a regular if it's not orthogonal to any roots. You can prove that this H must exist. Okay, so just believe me. And you can define a phi H to be a vector set of vector belongs to Rn such that the inner product with H. Sorry, you take the roots belongs to phi. So this root system is a set of vectors such that you define phi H such that this V belongs to phi such that this VH inner product is greater than 0. These are called plus. Okay, so these are called the element between these phi H plus are called simple or positive roots. Okay. Okay, so now let me give a very important definition called simple roots. So simple roots is a subset of phi H plus. So if I say alpha is a simple root, if alpha cannot be written as sum of positive roots. Okay, so you take out some subset of these positive roots and you call them simple roots if this alpha cannot be written as a sum of the positive roots. Okay, so from this definition, you can easily see that simple roots, so set of simple roots will span phi H plus. So any positive roots is sum of the simple roots. Okay, so this is still not as important. The important is the next. Okay, so lemma. This lemma tell you that any two simple roots and two simple roots, substance, a right or obtuse angle. Okay, so simply speaking is that you take any two simple roots, alpha and beta, their inner product must equals to 0 or less than 0. Or just simply say that their angle, so angle between alpha and beta must be either pi over 2, 2 pi divided by 3, 3 pi divided by 4, 4 pi divided by 5 pi divided by 6. These are all possible cases. Okay. By the way, yeah, pi is not allowed, right? Because if beta is negative alpha, then they are not simple roots. Okay, so proof. Okay, so by 3. So there is a by 3, we know that sigma alpha beta is defined to be, let's go back and see this, right? So it's beta alpha beta alpha alpha beta alpha. So it's a beta minus 2 alpha beta alpha alpha alpha. Okay. So let's check the following. Okay, so we have this. So let me just claim that if angle between alpha and beta, this is angle. If angle between alpha and beta is acute, is less than pi over 2, then alpha minus beta and beta minus alpha are roots. Okay, so what I'm saying is that if you take, let's say you take two roots, so you take the two roots, it's not necessary simple. If you take any two roots, alpha and beta, and if angle is less than pi over 2, then alpha minus beta and beta minus alpha are roots. Okay, so you can also check that. Let's do this. If it's greater than pi over 2, then alpha minus beta and beta minus alpha are not roots. Okay, so let me just quickly go through a proof. Let me just prove a simple case, right? Suppose you take, this is half. Suppose you take its half. So let me just let's assume that alpha and beta are 1. So let's normalize it, and it's 1. And then you can see that your sigma alpha beta equals to beta minus 2 times 2 alpha. Right? So it's beta minus alpha. Okay, so beta minus alpha is roots. And then if you do the reverse, you can show that alpha and beta are roots. If there is a negative here, then the alpha minus beta or beta minus alpha are not roots. Okay, so this is very simple, and the rest you can try to prove it. Okay, so why this is important? Because if alpha and beta are simple roots, and their angle, say the alpha beta is acute, less than pi over 2, then alpha minus beta are roots. Okay, or and also beta minus alpha are roots. Okay, but this is contradiction because we know that alpha and beta both belongs to phi h plus. So basically tell you that alpha h greater than 0 and the beta h are greater than 0. Okay, and also notice that alpha minus beta are also roots. Okay, so if you combine these two, then either alpha minus beta h is greater than 0, or beta minus alpha h in the product with h is greater than 0. You can obviously that one of it must be true, because alpha and beta and h cannot be 0, because alpha h cannot the same as beta h, because h is regular. Okay, so this is very important. So which tell you that if this is if it's greater than 0, then alpha minus is a positive root, which tell you that alpha can be written as alpha plus. Means that alpha can be written as beta plus alpha minus beta, or beta equals to this. So for example, if alpha minus beta is positive, then the alpha equals to beta plus alpha plus beta, which simple roots will become another two positive roots, which is contradiction. Okay, so this show that this lemma tell you that we prove this lemma. So any two alpha beta are any two simple roots must subtend the right or absolute angles. These are very important. Okay, so this is our powerful tool. Okay, so now we can talk about so-called admissible configuration. Definition: admissible configuration. Okay. So admissible configuration is a collection of univectors. In Rn. A collection of univectors are in an open half plane. Okay, so this is the same as there is this H is a vector in Rn, and all the vector that's called this admissible configuration phi, and that is phi can be so I should say all the vectors. So there is H belongs to Rn such that phi is a subset of all the vectors in Rn such that VH is greater than 0. Also what their angle can at most have 4 possible cases. Also their angle also their angle can at most be 3 pi divided by 4, 5 pi divided by 6. Okay, so these are called the admissible configuration. Okay, so by previous theorem, so which we just showed, simple roots. After you do the normalization, so simple roots forms admissible configuration. Okay, so once we have this, then the next time we can just do the classification of this admissible configuration. And then we can show that all the possible admissible configuration are all in this so-called thinking diagrams. And the next time I will introduce the powerful tool to classify such objects.